Uh, so my field of work is artificial intelligence, and since I started, I've been asking myself how can we create truly intelligent systems? So part of my brain is always thinking about the next roadblock that we're going to run into. Why what we understand how to do so far is going to break when we put it in the real world. What's the nature of the breakage? What could we do to avoid that? How can we then create the next generation of systems that will do better? But more recently, I've also been asking myself a question that I had in the first edition of my book, which is, what if we succeed? So that was back in '94. And in '94, I was, it was a fairly balanced picture that, the benefits for mankind could be enormous, but there were potential drawbacks. Even then it was obvious that success in AI might mean massive unemployment and so on. And then the question of control, right? If you build systems that are smarter than you, it's obvious that there's an issue of control, right? And you only have to imagine that you're a gorilla and then ask, should my ancestors have produced humans? From the gorilla's point of view, that probably wasn't such a great idea. So, but I would say in '94, I didn't have a good understanding of why exactly we would fail to achieve control over AI systems. I mean, people draw analogies, for example, to gorillas and humans, or to humans and superior alien civilization. But those analogies are not exact, because the gorillas didn't really consciously design the humans, and we wouldn't be consciously designing the alien civilization. So I asked myself, what is the nature of the problem, and can we solve it? Because I would like to be able to solve it. The alternative to solving the control problem is to, in some way, either put the brakes on AI or prevent the development of certain types of systems altogether if we don't know how to control them. That I think would be extremely difficult, because there's this huge pressure, right? We all want more intelligent systems. They have huge economic value. I think Bill Gates said, if you can just solve the machine learning problem, that's worth 10 Microsofts, which at that time would be, then that would come to about $4 trillion. So, $4 trillion is a decent incentive for people to move technology forward. So those are, those two questions: how can we make AI more capable, and what if we do, and what can we do to make sure that the outcome is beneficial? Those are the questions that I ask myself. And another question I ask is, why do my colleagues not ask themselves this question? Is it just sort of inertia that a typical engineer or computer scientist is in a rut or on the rail of moving technology forward, and they don't think about where the railway is heading, or whether they should turn off or slow down, or am I just wrong? Is there some mistake in my thinking which has led me to the conclusion that the control problem is serious and difficult? But so I'm always asking myself, am I making a mistake? And I go through the arguments that that people make for not paying any attention to this issue. And to me, none of the arguments hold water, and they fail in such straightforward ways that it seems to me that the arguments are coming from a defensive reaction not from taking the question seriously and thinking hard about it, but not wanting to consider it at all, because obviously it's a threat. You know, if you're, and I think we can look back at the history of nuclear physics, where you know, very famous nuclear physicists were simply in denial about the possibility that nuclear physics could lead to nuclear weapons. I mean, it's the idea of a nuclear weapon was around since at least 1912, I think, was when H.G. Wells wrote The Shape of Things to Come, which included what he called atomic bombs. He didn't quite get the physics right. He imagined bombs that would explode for weeks on end, so they would liberate an enormous amount of energy, but not all at once over a long period. So they would lay waste gradually to a whole city. But the principle was there, and there were famous physicists like Soddy who understood the risk and agitated to think about it ahead of time. But then there were other physicists like Rutherford who simply denied that it was possible, that this could ever happen. And he denied it was possible up until the night before Szilard invented the nuclear chain reaction. So, you know, the official establishment physics position was it could never happen, you know, and it went from never to 16 hours. And I don't think the same thing could happen with AI, because I think we need more than one breakthrough. I mean, you know, even arguably Zilard's breakthrough, that figuring out that you could make a chain reaction with neutrons, which did not get repelled from the nucleus in the same way that protons do. That was the key breakthrough, but it still took a few more years, but not very many, 5 to 6 years, before a chain reaction was actually demonstrated. You know, 5 to 6 years is an incredibly short time. And if we had 5 or 6 years to the point where there were super intelligent AI systems out there, we wouldn't have a solution for the control problem. And I think we might see negative consequences. If we were lucky, they would be contained. And that would be an object lesson in why not to do it. Sort of like Chernobyl was, you know, a medium-sized object lesson in why it's important to think about containment of nuclear reactions. I mean, I can't claim to have thought too much about containment and control early on. I've been doing AI. My first AI project was a chess program in 1975 in high school, and at that time, I mean, I read a lot of science fiction growing up. So, you know, I'd seen 2001 and so on. So the idea of machine intelligence getting out of control, and you know, there are Star Trek episodes and all kinds of things. So the idea has been around for donkey's years in popular culture. So I knew about all that, but I think I was, you know, a pretty straightforward techno-optimist in my youth. And no, to me, the challenge of creating intelligence was just fascinating and irresistible. The history was, I studied computer science in high school, wrote a chess program, was very interested in machine learning, read some AI books. Didn't think that AI was, at that time, a serious academic discipline. You know, I wanted to be a physicist. So I studied physics as an undergrad, and then I learned that, in fact, there was a possibility that you could do a computer science PhD and study artificial intelligence. And so I applied to PhD programs in computer science in the US, but I also applied to physics PhD programs in the UK, Oxford and Cambridge. And for various reasons, I just decided to take a break from physics. I had spoken to physics graduate students and postdocs and professors, and didn't get a very optimistic picture of what it was like to do particle theory. That you would spend a decade creeping up an author list of 290 people, and if you were lucky after umpteen years of being a postdoc, you might get a faculty position, but you might end up being a taxi driver instead. So this was, so I graduated in 82, and there wasn't that much going on. It was just before string theory became popular. People were looking for grand unified theories of physics, not finding anything very promising or even testable. And I remember very clearly a conversation I had with Chris Llewellyn-Smith, who was on the faculty. That was shortly before he went to be director of CERN. And of the people that I had met and taken classes from at Oxford, he was the brightest, very engaging, very intelligent man. And I had a meeting with him, and I asked him, what was he working on? And he said he was working on taking all the grand unified theories then in existence, of which there were 81. He was converting them all into mathematical logic, which I knew about, having studied a little bit of AI. And then in mathematical logic, it would be possible to directly compare two theories to tell if they were actually equivalent to each other or different, and whether they had testable consequences. And I think that was a relatively new idea for physics, to actually do that, not by just arguing, but actually mathematical proof. And I think he had got through 64 of the 81 theories, and it turned out that there were only 3 distinct theories. So all these people were producing theories, not even realizing they were the same theory as everybody else's. And 2 of the 3 theories were, in principle, untestable, meaning they had no observable consequences on the universe at all. And the third one could be tested, but it would take 10 to the 31 years to see any observable consequence of the theory. So that was a pretty depressing conversation for me. And I think that probably tipped the balance, along with sort of the mood of the grad students and postdocs, towards going into computer science and going to California. So after I arrived at Stanford, so I would say I hardly met any computer scientists. I had worked for IBM for a year between high school and college. And they had some very good computer scientists where I worked. And I did some interesting things there. So I think that gave me more of a sense of what computer science was like as an intellectual discipline, the kinds of problems people worked on. I met Alan Bundy at Edinburgh, because I also was admitted to the PhD program at Edinburgh, which was the best AI program in the UK. But by and large, people advised me that if I got into Stanford or MIT, I should go to Stanford or MIT, and I got into Stanford, despite applying 6 weeks after the deadline. They were very kind to consider my application anyway. So when I got there, my first advisor was Doug Leonard. So he, so several faculty had given their spiel at the beginning of the semester saying, here's what I work on. I'd love to have PhD students join the group. And Doug was just incredibly upbeat and optimistic, and really working on cool problems. He described a little bit his Eurisco system, which was a sort of multi-layered machine learning system, which was intended to sort of be able to grow into an arbitrarily intelligent system. So Doug was very ambitious, and I liked that, so I worked with Doug for a while. Unfortunately, Doug didn't get tenure. His ideas were maybe a little too ambitious for most of the academic community, and so some people did not see enough rigor or clarity in his papers and experiments. And so he didn't get tenure. I then worked with Mike Genesareth, who was a much more mathematically rigorous. He really liked every paper should have theorems, and he wanted to build a very solid set of capabilities and concepts. But he still had, the grand ambition of creating truly intelligent systems. But also he was interested in creating useful technologies for machine diagnosis, automated design, things like that. Well, I interacted some with Zohar Manna, who's more of a computational logician, interested in verification synthesis using formal logic. So I absorbed a lot of interesting ideas from him, although he wasn't particularly interested in AI, so it didn't quite match. There was a time when I was trying to have Doug Leonard and Zohar Manna as my two thesis advisors, and they just didn't see eye to eye at all, so it didn't really work out. 82 was when I went to Stanford. So Feigenbaum was there. And Nilsson was at SRI down the road. Minsky, I think, had somewhat dropped out of sight. He wasn't publishing actively. He had done the Frames paper in 76, I think, which had influence. But I think Stanford, as many universities do, they had their brand of AI, and they didn't really go to great pains to introduce students to everyone else's brand of AI. At Stanford, there was the heuristic programming project, which Ed Feigenbaum ran, which was very much about expert systems. Mike Genesareth was part of that, but had a more logic-based approach. Probability was viewed as not particularly relevant. There were arguments as to why you couldn't use probability to build expert systems. Probability. But it started to creep in through, largely I think through Eric Horvitz and David Heckerman, who were graduate students in the medical AI program with Ted Shortliff. And they had read about Yuda Pearl's work on Bayesian networks, or belief nets as they were called then. That I think was, I began to understand at that time how important that work was, and then when Pearl's book came out in '88, I was pretty convinced that what I had been told about probability was wrong, that it was entirely feasible to use probability, and in fact it worked a lot better than the sort of rule-based approach to uncertainty, which the Stanford group had been pushing. So I think, my thesis research was in the area of machine learning, but applying the tools of logic to understand what was going on in a learning system, and in particular, how a learning system could use what it already knew to learn better from new experience. And it seems to me that problem was crucial, and it is crucial today, because when humans learn, they bring to bear everything they know already to help them understand the new information. And so humans learn very quickly from often one or two examples of some phenomenon or a new type of object or experience that they might have. And current learning systems might need tens of thousands or millions of examples. And their design, current learning systems are designed to learn with no prior knowledge or very little prior knowledge, which is good if you know nothing, but that only explains possibly the first 5 minutes of a human's life. After that, the human already knows something and is already using what they know to learn the next thing. So tabula rasa learning isn't it? It's a good thing to study, but it can't be a good explanation for intelligence. Unless you can show that you just start with this blank slate and it, you keep feeding it experience and it becomes super intelligent, and we're not anywhere close to that right now. And if you think about what's going on with current learning systems, I know this is a digression, right? Think about what's going on with current learning systems. We're teaching them to learn to recognize, a sheep or an Oldsmobile, right? These are discrete logical categories. Mm-hmm. And we're doing that because it's useful for us to have sheep recognizers or Oldsmobile recognizers or whatever it might be. But if that's going to be part of a larger scale intelligent system, and if you're a deep learning disciple, you don't believe that deep learning networks use discrete logical categories or definite knowledge that sheep have 4 legs or any of those things. Well, why do you think that training a sheep recognizer is a step towards general purpose intelligence, unless general purpose intelligence really does operate with discrete logical categories, which at least introspectively we seem to. The first thing I did that, if you like, was considered to be a big deal outside of one branch of the machine learning community was the work on bounded rationality. So intelligence is, in my view, the ability to act successfully, and the ability to think correctly or learn quickly and so on. These are all, they have a purpose, which is to enable you to act successfully. To choose actions that are likely to achieve your objectives. And so that definition of intelligence has been around in the form of what economists would call rationality, what control theorists would call optimal control, people in operations research would call optimal policies for decision problems. And it's clear that in some sense that's the right definition for what we want intelligence to be. In AI, the definition of intelligence, if there is one, had been a restricted form of that, which is that you have a logical goal, I want to get to this place, or I want to construct this building, or whatever it might be. That's the definition of success. And an intelligent agent is one that generates a plan which is guaranteed to achieve that goal. And of course, in the real world, there are no guarantees, and there are trade-offs that you don't want to get to a place if it means dying along the way, for example. And so uncertainty and trade-offs, these are encompassed in the economic definition of rationality as maximization of expected utility. But it seemed to me that couldn't be the basis for AI because it's not computationally feasible. So if we set up AI as, we're the field that builds utility maximizing agents, then we're never going to get anywhere because it's not feasible. We can't even maximize utility on a chessboard. And a chessboard is, tiny, discrete, simple, well-known, fully observable slice of the real world. And we actually have to operate in the real world, which is vastly bigger. We don't know what the rules are. We don't get to see all of the world at once. There are gazillions of other players. And so the world is so much more complicated. And starting off with perfect rationality as your objective is just a non-starter. So I worked on coming up with a method of defining intelligence that would necessarily have a solution as opposed to being necessarily unsolvable. And that was this idea of bounded optimality, which, roughly speaking, says that, okay, you have a machine, the machine is finite. It has finite speed, it has finite memory. That means that there is in fact only a finite set of programs that can run on that machine. And out of that finite set, one or some small equivalence class of programs does better than all the others. And that's the program that we should aim for. That's what we call the bounded optimal program for that machine, and and also for some class of environments that you're intending to work in. And there we can actually make progress, because we can start with very restricted types of machines and restricted kinds of environments and solve the problem. That's actually show here is, for that machine and this environment, here is the best possible program that that takes into account the fact that the machine doesn't run infinitely fast. It can only do a certain amount of computation before the world changes. And I think that basically reading a lot of philosophy when I was younger was very helpful in coming up with these ideas, because one of the things that philosophers do is they look for places where you're confused or where there's some apparent paradox, and they say, okay, how do we resolve this? We step back and we say, okay, we're confused or we have a paradox because we have bought into a bunch of assumptions about what problem we're supposed to be solving, and we're actually not, we can't be doing the right thing if we run into these conceptual roadblocks. So how do you step back and change the definition of the problem? So what we had been doing was trying to define what is a rational action, and then, i.e. the utility maximizing action, and then saying, okay, that's the objective for AI, build systems that always choose the rational action. And in fact, with a bounded system, there is no notion of rational action that makes sense, because you're trying to ask the question, okay, what am I supposed to do if it's impossible for me to calculate what I'm supposed to do? Right? Well, that question doesn't have an answer, right? And it doesn't have an answer because the notion of rational action does not make sense for bounded systems. You can only talk about, what's the configuration that I should have, so that on average I'll do best when I'm faced with decision problems in the real world. No, I was aware of Kahneman and Tversky. I was in fact aware of it even as a grad student. I mean, their critique of rationality is an empirical one, claiming that, look, here are all these experiments showing that humans aren't rational in the classical sense. But that doesn't solve the problem from the point of view of AI. What should AI be aiming for, right? We're not aiming to copy humans. And a lot of what humans do is just a consequence of evolutionary accident. There's no assumption that humans are the pinnacle, that there is no better way to configure a human brain than the way nature has done it. But nowadays, I think actually a lot of people are reinterpreting evidence of human irrationality as actually evidence of human bounded optimality. That at least if you make enough assumptions, you can show that the so-called mistakes that humans make are the consequence of having a program, if you like, that's very well designed given the limitations of human hardware. And you would expect the program to make that type of mistake. And it does seem that humans are, so another part of my work at that time was, okay, so if bounded, if you can't do an infinite amount of computation, then what computation should you do? And so that led to what we call rational meta-reasoning, which is roughly speaking that you do the computations that you expect to improve the quality of your ultimate decision as quickly as possible. So you can apply this to a chess program and use it to control the search that the chess program does. It's looking ahead in the game, and you can look ahead along billions of different lines in the game. But a human, from what we can tell, is only looking ahead along a few dozen lines, if that. how does the human choose what is it worth thinking about, right? That's the question. What is it worth thinking about? And obviously, it's not worth thinking about, well, if I make this really good move and my opponent does this really stupid response, well, why think about that? He's not likely to make that stupid response, and so it's not worth my time to think about how I would win the game if he did that really stupid response. So humans naturally do this. When you learn to play chess, you don't learn, okay, well, here is the alpha beta tree search algorithm, and in order to play chess, you need to learn this algorithm for how to allocate your thinking time to various branches of the tree. It's just natural that our brains know or learn very quickly how to allocate thought to different possibilities so that we very quickly reach good decisions. And so I figured out how to do that, and showed that you could apply this technique of rational meta reasoning to control things like game tree search and get very good results without even designing an algorithm, right? And so there was sort of a background picture, which is I still don't think that we should think of AI as a collection of algorithms, right? An algorithm is a highly engineered artifact for a specific problem. We have very highly engineered algorithms for two-player games, right? When you go to a three-player game, you need a completely new algorithm. The two-player game algorithms don't work, right? When you go to a game like backgammon, where it's a two-player game with chance, right, with the dice rolls, again, you need a completely new algorithm because the two-player algorithm doesn't work. But humans don't operate that way, right? You know, you learn to play chess, you learn to play backgammon. You don't need some engineer to come along and give you a new algorithm. So it must all flow from some more general process of controlling your deliberations and your computation to get good decisions quickly. And so that, if you maybe you just want to say it's sort of one algorithm, but it's an algorithm that figures out what is the value of the possible computations I could do, and then does the most valuable one, and that's the algorithm. That's it. And the same algorithm operates across all these different kinds of games, you know, single agent search problems, two-player with chance, multiplayer, you know, planning problems. The same principle applies. And so I think, so those were the two things, you know, understanding this notion of bounded optimality as a formal definition of intelligence that you can really work on, and then this technique of rational meta reasoning. So those were the two things that I worked on in the late 80s and early 90s that really, I think, are, you know, the contributions from that period that I'm most proud of. And then, you know, having thought a lot about rationality and intelligence, I decided I had to write a textbook because I wasn't seeing these notions clearly laid out in the existing AI textbooks, which tended to be, okay, well, there's this field called natural language processing, so I'll tell you all about that. There's a field called search, so I'll tell you about that. There's a field called game playing, I'll tell you about that. And there was no unifying thread. There was no overarching integrating framework. So I wrote the textbook to say it's all rational agents or bounded rational agents. And the particular methods that are developed in search or game playing or planning are responses to particular additional assumptions that you make about the environment and how rational decision making occurs under those assumptions, right? So in search problems, we assume that the world is fully observable, that it's deterministic, that there's only one agent, and so on and so forth. And under all those assumptions, then search algorithms make sense. But they're all just a special case of rational decision making. I mean, I had written some notes for my undergraduate class, and I think they were up to about 200 pages. You know, they weren't particularly intended to become a book. It was just that I found what I was lecturing to be departing more and more from what the existing textbooks said. And I was actually quite worried that, you know, this was also a period, so the AI winter began around 88. The one I was exchanging email with at the Aspen Institute about this just yesterday, because they had used the word AI winter to refer to the one that happened in the late 60s, early 70s. And so the AI winter, the phrase came, I think, with Hector Levesque in 86, wrote a little paper saying the AI winter is coming. And the AI winter came from the phrase nuclear winter, which, as far as I can tell, was coined in 83, because the National Research Council did a big study on potential effects of a major nuclear war on the climate. So that was where the nuclear winter phrase came from. So I think AI winter per se, with that name, the first one was the late 80s. So that was after the collapse of the expert system industry. And, so after that, funding kind of dried up, students kind of dried up. And I was really quite worried that the field was going to fail. And part of it was that we were still using textbooks that had been written in the 70s or early 80s, and were not really capturing what we, by that time, so Pearl's book came out in 88, right? So by that time we actually had Bayesian networks, which solved a lot of the problems that caused the expert system industry to fail. I think there were a number of reasons why the expert system industry failed. So what they were doing was the following. They said, okay, there's lots and lots of knowledge work in our economy. It's expensive. Experts are hard to come by. They retire, they disappear. So there's a huge economic niche in building knowledge-based expert systems. And the way you build a knowledge-based expert system is you interview the expert. You essentially ask him to describe his reasoning steps, and you write them down as rules, and then you build a rule-based expert system which sort of mimics the expert's reasoning steps. And unfortunately, I don't think it really works that way. So everyone appreciated that in many of these problems, not all, but in many of these problems, there is uncertainty. Medical diagnosis is the canonical example. And everyone thought of medical diagnosis, partly because of the way it's taught in medical school, as if you have these symptoms, then you have this condition, or this, and if you have this condition and this other thing, then you will, then you'll go on to develop this other condition. And so they said, so the reasoning process was assumed to be from symptoms to conclusions, to diagnoses. And so they wrote rules in that direction. And of course, from any given set of symptoms, you can't conclude definitively that a person has a particular disease, like Alzheimer's, for example. And so there has to be uncertainty involved. There has to be some method of combining evidence to strengthen conclusions, disconfirming evidence, and so on and so forth. And so they essentially had to make up a kind of calculus for handling all this uncertainty, which was not probability theory, because probability theory doesn't admit of rule-based reasoning steps. Right? In fact, it's one of the main things Pearl did in his book, was to explain why chaining of rules cannot capture what probability theory says you should do with evidence. And so what tends to happen with those systems is that, with a small number of rules, you can tweak the weights on all the rules so that on the set of cases you want to be able to handle, it behaves correctly. But as you get to a larger range of cases and more rules and deeper levels of chaining, you get problems of overcounting or undercounting of evidence. You get problems where you end up concluding with much higher certainty than you really want that such and such is true, because the rules essentially operate a kind of pumping cycle where they gain more and more certainty because of their own cycles in the reasoning process. And so I think what happened in practice is that companies found it increasingly difficult as they built larger expert systems. They were more and more difficult to get right and to maintain. There were other reasons as well, like you had to buy a symbolic list machine to run these packages. You couldn't integrate it with your other data processing hardware and software. You had to hire special AI programmers who knew how to program in Lisp and this kind of thing. So there were many reasons, but I think the main one was the technology was flawed technically. Another interesting issue is, is human knowledge really in the form that people thought it was, which was these rules that you chain forward from the evidence with, adding uncertainty as you went along. And it turns out, I think, to be quite difficult to interview people and get those rules out. Whereas if you ask the opposite question, not if you see symptoms A, B, and C, what disease do you conclude with what certainty? If instead you ask, if a person has this disease, what symptoms do you expect to see? Right? That's in the causal direction. And this is how an expert actually understands health and disease, right? They think about, well, this microorganism lodges in your gut and causes this to happen, and that's why we see, bleeding through the eyeballs or whatever it might be. And so when Horvitz and Heckerman were interviewing experts, they found that they could extract these kinds of causal conditional probabilities in the direction from disease to symptoms very, very quickly, that it was very natural for the expert to estimate these. And also those probabilities turn out to be very robust. So if you think about it this way, right, if a person has meningitis, then there's a causal process that leads them to have certain symptoms. And that causal process is independent of who else has meningitis, right? It's independent of, the size of the population of patients, etc. But if you look at the other way around, right? So meningitis gives you a stiff neck, right? Well, if someone has a stiff neck, what's the probability that they have meningitis? That depends. I mean, is there a meningitis epidemic going on, right? Why is this patient in my office in the first place, right? Were they feeling just really poorly, or did they have a stiff neck because they got into a car crash? The probabilities that you can assess in the causal direction turn out to be much more robust. They are valid in a much wider range of circumstances than the probabilities in the diagnostic direction, because though whether that probability is valid, whether you have meningitis, given that you have a stiff neck, is highly dependent on other circumstances outside of the individual person. And so all of those issues, I think, conspired to make the expert system industry fail, and it failed pretty quickly. So what happens in these things is that technology comes out, and it's happening now with deep learning. Right? Everyone says, if I don't get hold of this technology and build up, a group within my company that knows how to do it, knows how to use it, then I'm going to be left behind. So they start investing in the technology without any evidence that it actually works to solve their problem, just as a sort of, on the assumption that if they don't, they'll be left behind, that there's a potential gain here, we can't afford to lose it. And so they're all sitting there, and maybe after 6 months or a year, they're still waiting for any return on their investment whatsoever. And then they start to hear stories that, this other company, they tried 6 times, and it just fails, right? It didn't work for their problem. It doesn't work for this, doesn't work for that. So then they start to lose faith very quickly. So all those companies that haven't yet had a success with the technology can switch overnight from thinking it's essential to maintain our competitive edge to, we better get out of this, otherwise we're going to look foolish. And so that's sort of what happened with the expert system technology in the late 80s, which is a shame, because by then, right, we already had the technological solutions that would have alleviated a lot of those difficulties. Yeah. It was tough. I mean, I remember going to a dinner in '93 with a bunch of Wall Street people, and I was sort of the odd person out. I was explaining they worked on artificial intelligence, and And it was like I was working on cold fusion. AI failed, right? It's like it doesn't exist anymore, right? As if somehow AI and rule-based expert systems in the commercial marketplace are the same thing. And so in the mind of Wall Street, the investor community, it doesn't exist, right? Their view was forget it. Where, of course, the field, academic field, was still pushing ahead. As I mentioned, I wrote a textbook that came out in '94, late '94, that tried to incorporate as much as we knew about how to use the rational agent framework, and then a lot of probability decision theory. This is with Norvig. So Peter Norvig is my co-author. And so to come back to the story about how he got involved. So I had some course notes, and Peter was back in Berkeley from time to time. I think he was working at Sun he had been at USC, he had come back to Berkeley, he had then gone on to Sun in Boston. They had a research lab there. But we had discussed when he was at Berkeley with Robert Walensky, who had been Peter's advisor, that we might try to write a Berkeley AI book. And Robert Walensky had his view on AI. He was a student of Roger Schenck, and after a while, although I really enjoyed Robert's company, unfortunately he passed on a few years ago, we just couldn't see AI eye to eye on the content. I mean, we just thought about the field in such a fundamentally different way that there was no way to get that to work. And he had a strong personality. It just was there was too much conflict. Whereas Peter is an incredibly easygoing person, and I think that's one of the reasons why he's so successful. He does not try to project his ego or his ability at all, and he's completely reasonable. You can have a discussion with him, and he doesn't feel threatened, and he doesn't try to threaten you, and it's very productive. He's also a really good writer and a great programmer, so we spend a lot of time writing code together to go with the book. So that was another important thing we did with the book, was to try to build a suite of code that was as fully integrated as possible to reflect the principle of the book, that rational agent framework was general. And I think we succeeded to some extent. It was not perfect, but it was a step forward. So I think the book helped to bring, what Pearl had done, for example, and some other ideas. Reinforcement learning also came out in the late 80s, but was not widely known or taught. So the whole notion of a Markov decision process was unknown to most AI researchers. So we tried to build these bridges showing that AI was really continuous with statistics, with operations research, which studies Markov decision processes. So decision making under uncertainty is what they do. In economics, studying utility theory, how do you construct these functions that describe value? So we tried to bring all of that in and create these connections to other fields. And I think that was really helpful for the field. I think it helped the field to grow up a bit, to realize that there's more to doing research than reading one paper in last year's proceedings and then doing some variation on that there's actually huge literatures in all of these other fields that are relevant to some of the problems we care about. So that was 94, and the book was unreasonably successful. So it's an interesting story. I mean, the issue of risk from intelligent systems and goes back to the very, the prehistory of AI. I mean, the word robot came from a play, a Czech play in 1920, and in that play, machine servants rise up and take over the world. So there has never been a time when existential risk hasn't been a thread in the field, and Turing talked about it with, I don't know whether you could say resignation or just blasé. He just says, yeah, well, when all this AI stuff starts to work, well, we'll be lucky if they keep us as pets. The intelligence explosion idea, which came, that phrase came from I.J. Good in a paper he wrote in '65, pointing out in particular that sufficiently intelligent systems could then do their own AI research and hardware design and produce their next generation very quickly, and that process would then accelerate, and the human race would be left far behind. And people look at that and they say, yeah, that sounds right, and then they just go back to work as if the actual semantic content was irrelevant. Minsky pointed out that if you ask a sufficiently intelligent machine to calculate as many digits of pi as possible, which sounds very innocuous, then in order to do that, it will take over the entire planet or even the reachable physical universe and convert it into a machine for calculating more digits of pi. And this was the point, so Norbert Wiener wrote a paper in 1960. So he had seen Arthur Samuel's checker playing program, which learned to play checkers by itself, by playing itself, and became more competent at checkers than Samuel was. So that was the very early proof in 57, 58 that one of the objections to AI, which is the machine can never do any more than we program it to do, that was sort of just completely misconceived, that machines can surpass their programmers if they're able to learn. And so Wiener, I think, was at a stage in his life where he was thinking a lot about the impact of technology on humanity and whether this was going to be a successful long-term future if we followed along the current path. And he said, he used the Sorcerer's Apprentice as an example. If you put a purpose into a machine, you better be absolutely sure that the purpose is the one that you really desire. And he says, this is going to be a major problem for, I think he was calling it automation at that time, but we would call it intelligent systems or AI. And we don't know how to solve it, but it's an incredibly difficult thing to even imagine how things are going to play out over a long future. But if we don't get it right now, we may have a long future that's not good. So we just have to try our best to figure it out. So I find that paper quite inspiring. I would say, generally speaking, the companies that are doing AI prefer not to talk about risk, because they don't want their brand, associated with Terminator robots, which is usually how the media portrays risk. It's a picture of a Terminator, and that's, of course, completely misleading, right? The media and Hollywood, the risk is always, well, somehow machines become spontaneously conscious, and as soon as they do that, they're spontaneously evil and they hate us, and then all hell breaks loose. And that's not the risk. The risk is just machines that are extremely competent, that are given objectives where the solution to those objectives turns out to be something that we are not happy with, which is the King Midas story or the Sorcerer's Apprentice story all over again. And that's exactly what Wiener was warning against. So in Britain in particular, there's this notion of the health and safety officer who who's appointed by the council and is kind of a busybody and goes into everyone's office and says, oh, you need to have those windows locked, or you need to have wider doorways, or whatever it is. But you just imagine the health and safety officer going back to a million years BC, where these poor people have just invented fire so they can keep warm and stop eating raw food. And the health and safety officer says, oh, you can't have any of that, it's not safe, you'll catch your hair on fire, you'll cause global warming, we're going to put a stop to this right now. And so a million years ago would be, too early to be trying to put constraints on technology. But with respect to global warming, I would say 100 years ago would have been the right time, or 120 years ago, right? So we had just developed internal combustion engine and electricity generation and distribution. And we could, at that time, before we became completely tied into fossil fuels, have put a lot of energy and effort into also developing wind power and solar power, knowing that we could not rely on fossil fuels because of the consequences. And we knew, right? Arrhenius, other scientists had shown that this would be the consequence of burning all those fossil fuels. Alexander Graham Bell wrote papers about it, but they were ignored. There was no vote. There was no, governments tend to get captured by corporate lobbies, and not so much the scientists. So you might say the scientists invented the internal combustion engine, but they also invented, or discovered the possibility of global warming and warned about it. But society tends to take the goodies, but not listen to the downside. Well, the people, I think, when genetic engineering got going in the 70s, most people, they didn't know what that even meant. Most people didn't even know what DNA was. I think had it been fully explained, they probably would have gone along with what the scientists decided, which is that, number one, we need to enforce fairly stringent safety constraints on these kinds of experiments so we don't accidentally produce disease organisms that infect people. And number two, we're not going to allow experiments that modify the human genome. And that's what they did. And I think they were pretty praiseworthy. I think what they did was really impressive, given that for a long time, one of the main purposes of genetics was precisely the improvement of the human stock, as they used to call it. Good old-fashioned eugenics, which was mostly born in California, I think, and then exported to Germany in the 30s. That was one of the main purposes for doing all this research. So for them to say, okay, now we could actually do it, but we're not going to because the social consequences are undesirable, I thought that was pretty brave. It would have been interesting to have a real public debate. I believe they did not allow journalists at that meeting, the SLMR workshop that they held. The new meeting, which was precipitated by the new capabilities of CRISPR, came to the same conclusion, but it's a more leaky situation now, right? There are too many scientists. Yeah. There are countries where there's much less of a moral concern about modifying humanity. But so I think it's always very difficult for a democracy to decide on what the right regulations are for complicated technological issues. How should we regulate nuclear power? How should we regulate medicines? And often the regulation follows some catastrophe, and can be poorly designed because it's in the middle of outrage and fear and so on. So I would much rather that when we think about AI, that we think ahead as far as we can. And realize that the right thing to do is not to try to hide the risks And I see, for example, the AI 100 report, which just came out a couple of weeks ago, which, so Eric Horvitz set up this AI 100, 100-year study on AI at Stanford. And they're supposed to produce a report every few years, and so they assemble a panel of distinguished scientists, and they produce this report, which, it's intended to be a prediction about what kinds of impacts AI will have by 2030 on a typical North American person living in a city. What sorts of technologies will be available, what impact. And but they talk about risks, and basically they deny that achieving human level AI is even possible, which to me seems utterly bizarre. That if that's the official position of the AI community, then I think they should all just resign. Because the report says that there might be risks, but we shouldn't talk about them, because if we talk about them, that might prevent people from doing research on risks in order to prevent them, which is just doesn't make sense.